Hello everyone. This set of notes will cover part 1 of the chapter 5 material. We're going to start with section 5.1 and end with section 5.3 in this section. Section 5.1 is just a brief overview of isomerism. For example, you've heard of constitutional isomers, and we're going to introduce something new called stereoisomers. So there are two broad classifications of isomers, constitutional and stereoisomers. A constitutional isomer, like you saw before, was just a different molecule that has the same molecular formula, but a different connectivity of the atoms. A stereoisomer is simply, are simply two molecules that have the same connectivity, same molecular formula, but they have a different spatial arrangement of the atoms in the molecule. So that's going to be the main difference, is that spatial arrangement, and we're going to look at a few examples. The first type of stereoisomers we're going to look at are cis and trans stereoisomers. So the molecules shown here are cyclohexane rings with two methyl substituents on each one. As we can see, the molecular formula is the same. They have all the same types and number of atoms right between these two. Their connectivities are the same on both rings. We see that both rings have two methyl groups connected to the same exact carbons. However, what's different here is the spatial arrangement of the methyl groups on the carbon atoms or around the carbon atoms. In the first example, the methyl groups are on the same side of the ring, and in the second example, the methyl groups are on opposite sides. So same side is cis, opposite sides are trans. If we were to draw a bond line structure for these, our cis could have two wedges, or it could, if you flipped it over, it would be two dashes. But our trans isomer would have one wedge. Oh, actually, let me draw it the way that it's written here. The first one would be a dash, and the second one would be a wedge. So because we need to be able to differentiate these somehow, we have to use the term cis and trans when we name these. So you can see the cis and trans are used to describe the molecules in their IUPAC names. The next type of stereoisomer that has the same connectivity, same molecular formula, but a different spatial arrangement are cis and trans alkenes. So we can see that in our cis isomer, the methyl groups are on the same side, and in the trans isomer, the methyl groups are on the opposite sides. Again, we use cis and trans in the name to differentiate them. So the relationship between these two are that they are stereoisomers. And we're going to talk about the different types of stereoisomers later. We're going to look at the relationship between different molecules and try to classify them as either constitutional isomers, stereoisomers, or identical structures. So in our first example, let's call it A. We have two cyclohexane rings, both with alcohols attached. And we can see that the alcohol is on the top face of the ring. So these molecules both have the same formula, connectivity, and spatial arrangement. These are identical. In the second example, we have two molecules that have the same molecular formula, same connectivity, but the spatial arrangement seems to be different. In the first example, with the first molecule, the alcohols are both in the top face of the ring, so this is cis, and on the second example, the alcohols are on opposite faces of the ring, which makes it trans. So these are stereoisomers. That was B. We'll call this C. And in example C, we've got two molecules. It looks like they have the same molecular formula. They both have 1, 2, 3, 4 carbons and 8 hydrogens, but the connectivity is different. So these are constitutional isomers. In the next set of molecules, we'll call that D, it looks like we have, well, 2 carbons connected by a double bond, and we have methyl groups attached. The thing is, if I rotate this molecule or sort of flip it over like a pancake, I see that these are actually identical. And in the last example, we have double bonded carbons, and each carbon, right, has we have a methyl on the first carbon, we have an ethyl on the second, and they're opposite, so that means these are trans. And in this next molecule, we have the methyl and the ethyl on the same side, making them cis. So cis-trans relationship tells us that these are stereoisomers. In section 5.2, we're going to introduce different types of stereoisomerism. But first, we need to be able to identify molecules as chiral or achiral, and then be able to identify chirality centers. Chiral simply means that an object is not identical to its mirror image. The object is not superimposable on its mirror image. So what I mean by not identical to its mirror image is that it cannot be superimposed. So for instance, your hands are chiral because they do have a mirror image, but they are not identical to the mirror image because they cannot be superimposed. So non-superimposable mirror images mean chiral. Achiral means that your object or molecule has a mirror image, but the mirror images can be superimposed on each other. So superimposable mirror images means achiral, and non-superimposable mirror images mean that it is chiral. So chirality is important in molecules for pharmacology reasons. First of all, because, for example, different stereoisomers could be, one stereoisomer of a molecule could be biologically active and the other one could be totally inactive or even toxic. So this is, it's very important to be able to identify stereoisomers. So when we're looking at molecules, we need to be able to identify a chiral molecule. And we do that by looking for any carbon atom that has 4 unique groups attached. Let's take 2-butanol, for example. So here's our carbon, and it has an alcohol, it has a hydrogen attached, it has a methyl attached, and it has an ethyl attached. So this is a carbon with 4 unique groups attached to it. That makes this carbon, and therefore the whole molecule, chiral. And this molecule also has a mirror image. So if we were in class, I would build a model and show you that they're non-superimposable. But if you'd like, you could stop the video and try to make this with your model kits to prove it to yourself, that the mirror, build 2 molecules that are the same so that you see that build 2 molecules that have the same mirror image, right? So build this one, then build this one. You'll see that they're mirror images, but there's no way to superimpose them on each other. So we're going to talk about this, the stereochemical relationship between these very shortly. These are called enantiomers, but we'll get there. All right, so a chiral center is simply a carbon that has 4 different groups, right? We just defined chirality in a molecule as any molecule that has a carbon with 4 different groups attached. Now we're looking a little more specifically at the carbon atom itself, not the molecule. So chirality center, stereocenter, stereogenic center, or asymmetric center are all words that mean the same thing. If you look at our first one here, we've got a carbon that has a chlorine. No, don't forget there's a hydrogen there too. It has, this carbon has a chlorine that's different from a hydrogen, that's different from a methyl, that's different from an ethyl. So that makes this particular carbon a chiral center. Let's look at the next one. Our carbon has an OH. It's got a hydrogen, which is different than the propyl group, which is different than the ethyl group. So that carbon is a chirality center, and it makes the entire molecule chiral. On our next one, we have a carbon that is attached to a bromine, and don't forget there's also a hydrogen. So we had a bromine that's different from a hydrogen. Now when we go around the ring that way to the right, we see we hit a carbon that's double bonded. That is different than when we go around the ring this way, right? Do you see that going around the ring both directions is different? So that makes this chiral. All right, in this example, we're going to identify the chirality centers in the following molecules. So how do we do this? We're going to look for carbons with 4 different groups attached. So if you'd like to pause the video and try this on your own, you can do that and come back and watch my explanation, or you could just keep it rolling and watch how I do this. All right, so in our first example, we've got a carbon that's attached to an OH group, but here's the thing. Going around the ring that way is identical to going around the ring that way. Let me draw this in a different way for you. So this carbon has a hydrogen, it has an OH, but do you see that going around the ring to the left and the right is exactly the same? So this carbon here is not a chiral carbon. There are no chiral carbons in this molecule, therefore it is not a chiral molecule. In the next example, if we want to draw a bond line structure to help us see it better, all right, we can see that each of these carbons has a hydrogen and an OH. Let's start with the first one on the bottom here. We've got a hydrogen, an OH, right, on this carbon. And then going around the ring in both directions is actually different. We encounter different atoms and different connectivities. So that makes this carbon chiral. We'll put a star next to it. If we go to this one, the next one, we see that we've got an OH, an H, and then going around the ring in both directions is different. So this is also a chiral carbon. In the next example, we've got a molecule that seemingly, this one can be a little tricky because let's look at our first carbon here. We've got carbon that has a hydrogen, methyl, methyl, and then this whole, let's just say this whole group is one separate group, right? So essentially we're making each carbon look the same. So look, we've got that, that, and we need to have 1, 2, 3, 4 different things attached to characterize it as a chiral carbon. So we've got a methyl, we've got a hydrogen, oh look, there's another methyl, and then we have this whole big group. Well, in order to be chiral, it must have 4 different things attached. So this is not chiral, not a chiral center, not a chiral carbon, because of the 2 methyl groups attached, that and that. If it has 2 of the same groups attached to the carbon, it's not a chiral carbon. Let's look at the next one. In this example, let's look at our first carbon here. I've got an ethyl, I've got a methyl, don't forget the hydrogen that's in the back there, a hydrogen, and then this whole big group. So there are clearly 4 different things attached. So this is a chiral carbon. And let me clear this out and show you the next one. I'll just put a little star next to that one because we know that's chiral. Now for this carbon, we've got a methyl, there's a hydrogen, and then you got this whole group and this whole group, which are clearly different. So that makes that a chiral center as well. This molecule has 2 chiral centers. All right, and we're going to look at this bottom one here. We have 1 chiral center that has 4 different things attached, right? Don't forget there's also a hydrogen. Let's see, we got 1, 2, 3, 4, 5. Now, if you're wondering why this is not chiral, it's because this carbon has 2 methyls. Not a chiral center. So that is. So all the ones that are circled are chiral. All right, so we mentioned the word enantiomer before when we were discussing stereoisomers and what makes something chiral. Enantiomers are simply 2 molecules that are mirror images but are not superimposable. So you worked with the carbones in our polarimetry lab, R and S carbone. We can see that everything is identical except for the spatial arrangement of these substituents around the carbons that I just indicated. You see how that's a dash, and this is a wedge. Connectivity is the same, but their spatial arrangement is different. So really the trick to identifying enantiomers is that their stereocenter has been flipped. And if in one isomer, if in one isomer it's a dash, and then the other one it will be a wedge. So let's take a look at the example below. If we want to draw the mirror image, All right, we have this, and now if we flip this over, we get so now let's compare that and that. These are non-superimposable molecules. You can't superimpose this one on this one. That makes them enantiomers. So I'm going to show you how to quickly draw all of the enantiomers for a particular molecule. All right, the easiest way to do this is to just invert the chiral centers. So if a molecule is chiral, just invert the dashes and wedges of the chirality center to draw the enantiomer. So let's say I asked you to draw the enantiomer for the following compound. Say, okay, there's the chirality center. It's a wedge. If I want to draw the enantiomer, I'm going to draw the substituent as a dash instead. Just invert it. If it's a wedge, draw it as a dash, and then you've drawn the enantiomer. Let's look at the next one. If we want to draw the enantiomer of the following compound, identify the chiral center. We see that the methyl is a wedge, so if we draw it as a dash, then we've just drawn its enantiomer. In the molecule below, we actually have no chiral centers. Right? These are identical molecules. These are identical. Why? Because if you flip this like a pancake, it is superimposable on the first structure. Now, what if I have a molecule that has two chiral centers and I want to draw the enantiomer? So let me make something up here. Let's say that's a bromine, and let's say that this is an alcohol. Let's draw the enantiomer. All right, well, the trick here is to just locate the chiral centers. I've got 1, 2, and if it's a wedge, then we're going to draw it as a dash. So there's the first one. I just drew the substituent with a dash. And in our second one, the alcohol is a wedge, so I'm going to just draw it as a dash. So the relationship between these two are that they're stereoisomers, but also, more specifically, they are enantiomers. Right, the next skill you need to be able to do is look at a molecule and identify the number of stereoisomers possible for that molecule. It's really simple. The number of stereoisomers is going to be equal to 2n, where n is the number of chiral centers. So, if you look at the molecule that's on your slide here, we have 1, 2, 3 chiral centers. Each of those carbons has 4 different groups attached. So the number of chiral centers, or the number of stereoisomers, is going to be equal to 2 to the n. And n, in this case, is 3. We have 1, 2, 3 chiral centers. N is 3. So 2 to the third power equals 8. In section 5.3, we're going to discuss how to identify the configuration using the Cahn Ingold Prelog system. So since enantiomers are not identical, they shouldn't have identical names. So how would we name these? Well, their names technically, right, without, if you were doing this as we learned before in chapter 4, we would call this 2-chloro butane. But look, this one's also 2-chlorobutane. So how are we going to differentiate these? Well, we're going to do that using this Cahn Ingold Prelog system by assigning the stereocenter an R or an S configuration. Then we're just going to put that in front of the name. So this one turns out to be the R, and this turns out to be the S. All right, to identify the R or S configuration at a chirality center, we're going to go through the following 4 steps. First step is we're going to use the atomic number to prioritize the 4 different groups attached to the chirality center. So we use atomic number from the periodic table. Next, we're going to arrange the molecule in space so that the lowest priority group faces away from you. That's number 4. We're going to count our priority groups, 1, 2, 3, and determine if we're counting in a clockwise or counterclockwise direction. And then once we've identified the direction that we're counting, we just assign R or S based on it being clockwise or counterclockwise. So if you have a model kit, it's helpful to use that as a visual aid when you're doing these, but it's not necessary. Let's look at a few examples. Okay, if we want to identify the configuration of the chiral center here, step 1 is we're going to use the atomic numbers to prioritize our 4 groups. Well, chlorine has the highest atomic number. That gets a 1. Oxygen has the next highest atomic number. That's a 2. Carbon is the next highest atomic number. That's 3. And hydrogen is a 4. That's the lowest atomic number. So, step 1, we've assigned our priorities. Now, what I like to do is let's just make this molecule easier to look at. So I'm going to take this molecule, and we're just going to put 4 different groups just like it's drawn in the original molecule. But instead of drawing the substituents, I'm just going to put the numbers in. So I have 1, 2, 3, and 4. By doing this, it's going to allow you to make every single problem look the same and work the same. So you can take a very complicated molecule, but if we just focus on the chiral center and put in numbers instead of substituents, it makes things easier. Now, step 2 is that we need to make sure that our lowest priority group is actually in a dashed position. So what we'll do is we'll rotate this molecule. We rotate around this axis so that the number 4 position is in the back. Step 3 is we're going to count around and determine if we're going clockwise or counterclockwise. Remember, we're counting 1, 2, 3, and back to 1. So this is counterclockwise. So that makes this configuration for this chiral center an S configuration. Let me show you another way to do this. If you don't like the rotation that we did in step 2, I have an alternate method. It's called the switch trick. All right, so we only need to do the switch trick if our number 4 group is not a dash, if the number 4 is not pointing behind the plane. So instead of rotating like we did in step 2, we're simply going to switch the 4th priority group. We're going to switch number 4 with whatever happens to be behind the plane. So switch 4 with whatever is the dash. And then we just proceed from there. Now the trick is, if the switched version ends up being an S, then the original is R, and vice versa. If the switched version is an R, then the original will be an S. So let's do the same exact molecule that we did in the last example, but let's use the switch trick. So we have our chiral center. We know there's 4 different things attached. So we know that the chlorine is 1, oxygen is 2, the ethyl group is 3, and that hydrogen is 4. All right, I'm going to redraw this to make life easier. Don't want to put my substituents in here. And we're just going to put the numbers in. So that was 1. The wedge was 4. It was 3. And that was 2. Now, in order to count, to figure out your direction of being clockwise or counterclockwise, we need to have number 4 in the back. You see how number 4 is a wedge? That means it's coming out of the plane of the board. So we can't count around to determine clockwise or counterclockwise like this. So what we're going to do is, just like I said before, take whatever we need, number 4, and we're going to switch it with whatever is the dash. So we're going to switch 4 with the dash. That's number 1. Switch 4 with the dash. So I'm going to keep these the same. So we're keeping the structure the same. But because I'm going to swap these, I'm putting 4 here, and I'm putting 1 here. So now I'm going to just count around. 1, 2, 3, back to 1. You can sort of ignore number 4. Another way to think about this is like this. If you just pretend like, once you get 4 in the back, you can pretend like it's not even there anymore. One, two, three, 1, 2, 3. So the switched version, so I did my switch here. My switch version was clockwise, which means that's R. So if the switch is R, then the original must be S. So my chiral center has an S configuration. We're going to look at several more examples, and I'm going to use the switch trick for each of these. All right, we want to assign the configuration of the chirality center. This is our chiral carbon. So oxygen is going to be highest priority because it has the highest atomic number. Then nitrogen, then the carbon, and hydrogen is going to be the lowest priority. What we want to do is make each problem look the same. I'm going to draw my template and put the numbers in and forget about the actual substituents. All right, now I need number 4 to be in the back. I need number 4 to be a wedge. So to do the switch trick, I'm going to take my whatever number 4 is, and I'm going to switch it with whatever has the dash. So let's do the switch. I'm not messing with 1 and 3 here. So because number 2 was in the back, I need to switch 4 with that. So 4's got to go in the back, and I switch it with 2. So these are the 2 things that we're getting switched. All right, now I can sort of ignore the 4th priority. I'm going to count around 1, 2, 3, back to 1. This is counterclockwise. So my switched version is an S. That means that my original must be R. The next scenario we have to look at is when the groups attached to the chiral center are similar, or if they have the same atomic number. And this can be a little bit tricky to prioritize them and assign their 1 through 4 priority numbers. So what we're going to do is look at one layer at a time of the atoms. So let's look at the molecule here. Now, assigning number 1, that's pretty easy. Oxygen has a higher atomic number than hydrogen or carbon. Clearly, hydrogen is going to be the lowest priority because that has the lowest atomic number. Now we're just looking at our 2 carbons here. So what we're going to do is sort of imagine, look at this carbon right here is attached to a hydrogen, and another carbon. I don't really care about what's going on in this direction. Just look outward. We have a carbon, hydrogen, and a hydrogen. So I get a C, H, and an H. Now if we look at this, we have a carbon that's attached to a hydrogen, and it's got another carbon there. That's also a C, H, and an H. This is a tie. So how are we going to differentiate these two? Well, we have to go to the next layer. We're going to go out to the next carbon. So now we're focused on this carbon. Now I don't really care about anything going on in this direction. We have a hydrogen, and then we have carbon. So I have that carbon, hydrogen, and now let's look at this carbon right here. Who cares what's going on in this direction? Ignore that. I've got a carbon, it's attached to a carbon, and it's also attached to a hydrogen as well. So I've got carbon, and hydrogen. See, that carbon here is my tiebreaker. So essentially, we go out, and as the complexity of the group increases, that will help us to break the tie. All right, so let's determine the configuration on our molecule here for chiral center. Clearly, this is the chiral carbon. I've got an OH, which is going to be number 1. My hydrogen is going to be number 4. You see, I've got a tie. I've got 2 carbons. So I'm going to have to look at this one layer at a time. So the first layer is a tie. And the second layer, let's take a look. Our second layer is we have our carbon, all right, is attached to, remember we don't care about that direction. It's attached to a carbon, and a carbon. And look at the other one, we're attached to a hydrogen, and an O. So oxygen beats carbon because it has a higher atomic number. So in this case now, let's come back and make our template so that we can assign the configuration. So the oxygen was number 1, the hydrogen was number 4, and we decided that the left side beat the right side here. All right. So at this point, we want to make sure that our number 4 is in the back, and it's not. So let's do the switch trick. We're going to switch number 1 with number 4, right? Because we're basically just taking 4 and switching it with whatever is in the back, which is number 1. So 2 and 3 stay the same. So now 4's in the back. I have 1 in the front. Now we're going to count around. 1, 2, 3. You can sort of ignore that number 4 group in the back. The switched version was counterclockwise, which is S. That means that the original is R. So the configuration at my chiral center is R. When prioritizing, a double bonded group counts twice, so it counts as 2 single bonds. And a triple bond counts as 3 single bonds. Where this scenario arises is in a molecule where we have a chiral center, and we have 1, 2, 3, 4 carbon groups attached. So how do we deal with these, especially one that has a double bond in there somewhere? All right. So if you saw this right off the bat, the first layer is a tie because we have carbon, 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 and carbon. So we have to go to the second layer. Now in our second layer here, I've got, right, this carbon has a hydrogen, and a carbon. This one's got a carbon and 2 hydrogens. So that's the same. And this one has 3 hydrogens. Right. And this one has 2 oxygens and a hydrogen. So that's an O, an O, and an H. Right? Because the double bond counts as 2 single bonds. So if we make our just a little tally here, I've got a C, H, H for this one. This one was also a C, H, and H. This one here was a C, or sorry, was 3 H's, H, H, and H. And here we have a O, O, and H. So that's going to be our first priority. So if I draw my molecule again, we know that that group to the right is going to be our number 1 priority. Right. So this is number 1. Now we're left between a methyl, an ethyl, and a 1, 2, 3, 4 propyl group. In this case, we can just look at the complexity. So a methyl is less complex than an ethyl is less complex than what was that? 1, 2, 3, 4, a butyl group. So we're going to say that our methyl is number 4. The ethyl is going to be number 3, and my butyl is going to be number 2. So now let's redraw this. That way I can make every problem look the same. That's 3, 2, 4, and 1. Now 4 is not in the back, but 2 is, so I'm going to have to switch these two. Let's do that switch. 1 and 3 stay the same. But 2 and 4 we're switching. So we're going to count around. 1, 2, 3, back to 1. My switched version was clockwise, which means it's R. And if the switch is R, then the original must be an S configuration. Let's look at several more examples and try to assign R or S configurations for each of the chiral centers in the molecules. All right, so let's first find the chiral centers. Well, this first one, that is not a chiral center because that carbon has two methyl groups. So it's not chiral. But we do have a chiral center here. All right, so chlorine is going to be number 1. Oh yeah, don't forget you've got a hydrogen in there. That's easy. That's going to be number 4. And I've got this methyl group, and then this whole group here, that whole side, the whole left side of the molecule. Well, the left side is definitely more complex, so we're going to call that 2, and your methyl group will be 3. So let's make our template. Now in this case, number 4 is already in the back, so I don't have to do a switch. No rotations, no switches. All we're going to do is count around. So this original, which already had 4 in the back, I'm counting around counterclockwise. That makes this an S configuration. In the next molecule, we have 1 chiral center. Don't forget you've got a hydrogen. That's a methyl, CH3. All right, so our hydrogen clearly is going to be our lowest priority. Now we have to decide, should going that way, or that way be number 2? Well, the more complex set of substituents here is right here because I had a carbon and then a carbon with 2 oxygens. This is going to be number 2. This side's going to be 3, and that's number 4. Oh, wait a minute. Sorry, guys. That was number 1. So number 1, 2, methyl is 3, and the hydrogen is 4. So let's just make our template here so that each problem looks the same. We've got 2, that was 1, hydrogen was 4, and that's 3. Now we need to take whatever's in the back and switch it with 4. So we're going to switch 4 and 3. We'll keep 1 and 2 the same. Now 4's in the back, 3's in the front, so I just did my switch. And we're going to count around. 1, 2, 3. That's clockwise. So the switch version was clockwise, which makes it R. That means my original is S. All right, let's look at the next one here. We have our chiral center, carbon with 4 different things attached. Nitrogen has the highest atomic number. Don't forget you've also got a hydrogen attached there. That's easy. That's going to be 4. And I think you can see, hopefully, that this right side, that's going to be 2. And that's going to be 3. We can make our template. Now because 4 is not in the back, I'm going to have to do my switch trick. I'm going to switch 1 and 4. You just switch 4 with whatever's in the back. Two and 3 are staying the same. Now I'm going to count around. 1, 2, 3. And that's counterclockwise, so my switch is S, that means my original is R. For the next one, I think you can see the chiral center here. I've got a methyl, ethyl, 1, 2, 3, and a butyl, and a hydrogen. So that hydrogen is going to be number 4. The butyl is going to be number 1. The ethyl will be 2, and the methyl will be 3. So if I make my template, and this one's easy because number 4 is already in the back. Don't have to do a switch. All I have to do is count around. 1, 2, 3, back to 1. So my direction is clockwise, which means this stereocenter has an R configuration. In the next example, we have molecules that have 2 chiral centers. So we're going to have to assign R or S for both chiral centers. Let's start with our first chiral center here. The chlorine will be 1. The hydrogen in the back is going to be 4. Clearly this group to the right is more complex than the group on the left, so we're going to call this 2 and this 3. Now, we can shortcut here because 4 is already in the back, so I can count around 1, 2, 3. So this first chiral center, counting around clockwise, is an R. Now let's take a look at this one, this chiral center here. Chlorine is going to be 1. The hydrogen attached is going to be 4. We have this large group over here. We're going to call that 2. And this ethyl group, we'll call that 3. Now 4 is not in the back, so let's make a template for this chiral center. Four, 1, 2, and 3. So we're going to switch 4 and 1. Keeping 2 and 3 the same. We count around. 1, 2, 3, back to 1. My switch is counterclockwise, that's S. And my original is R. So this chiral center also has an R configuration. So I hope that you've seen so far that wedges and dashes don't mean R and S. You have to go through the process to determine the configuration. Just because it's a wedge, like in our leftmost chiral carbon, just because it's a wedge doesn't mean it's an R, because in the second one, that was a dash, and that was also an R. We're moving on to the next molecule. We've got to clean up some of these spots I have here. All right, we've got 2 chiral centers. Let's start with the first one here. First chiral carbon. Our nitrogen is going to be number 1. The hydrogen in the back is going to be number 4. My carbon connected to 2 oxygen, my ketone group here is going to be number 2. And I've got a carbon with a methyl and an OH, which is a lower priority than a carbon with 2 oxygens and a CH3. So this is going to be 3. So if I make my template, oh, I actually don't need to make a template, but I can do it anyway, just to clean it up. All right, 4 is already in the back, so we don't have to do a switch. So we count around 1, 2, 3, back to 1. It's counterclockwise, so that makes this an S configuration. My first stereocenter is S. I'll clean this up a little bit and we'll work on the next one. So now let's look at this stereocenter. My oxygen is number 1. The hydrogen going back is going to be number 4. The carbon with the attached to the nitrogen is going to be number 2. My methyl is going to be number 3. So let's make a template. Four, 3, 1, and 2. Now 4 is already in the back, so I'll just count around. And because I'm going counterclockwise, that makes it S. So that carbon also has an S configuration. All right, in our last slide here, which is going to conclude section 5.3 and conclude this part of the notes, all we have to do is assign configuration and then put it into the IUPAC name to distinguish one enantiomer from another. So let's take a look at the 2 enantiomers of 2-butanol. Remember, you can draw all the enantiomers by just flipping or inverting the wedge or dash. All right, so this one happens to be, the first one happens to have an R configuration. And the second one happens to have an S configuration. Now to name these, right, these are both forms of 2-butanol. The R, you just put the R in parentheses, put it out in front, and the S goes in parentheses, and you put it out in front. And what if you have 2 stereocenters? Well, we need to tell the reader that at carbon 2, the configuration is an R, and that at carbon 3, the configuration is an S. So we do that by saying 2R, tell the reader that at the second carbon, it's an R configuration of the chiral center, and at the third carbon, you also have a chiral center with an S configuration. And then you just name the rest exactly as we would before. All right, so that concludes the set of video notes for sections 5.1 to 5.3.